So we talked yesterday about how we could have this relationship between one switch and two switches and form that port channel, okay? That logical port based on those two physical port members in this example, right? So when we do this, we have a one-to-one relationship. We have a stipulation that we have to do this between two switches, okay? Now, us as network engineers, we like to multi-home stuff. We like to add redundancy to our network, okay? Not a lot of other fields appreciate redundancy quite like we do in the networking field, right? But we have these two devices, but we still have, we have multiple links. We have logical link for spanning tree to flow over, but we still have two devices, okay? So one of these goes down, we still lose the link altogether, right? So we came up with this concept and we're like, how could we go about adding redundancy to our port channels? And they came up with this name, multi-chassis ether channel, or just MEC for short, right? So what they did is they developed several technologies that allow us to utilize multi-chassis ether channel, okay? Can you guys think of some of those technologies or those, I guess I could say, functions that allow us to do multi-chassis ether channel prior to VPC? So I'm strictly thinking before VPC came along. What could we use to do multi-chassis ether channel? Any ideas, guys? Right, Juan's got one. We could use virtual switching system, or VSS for short. There's also another, real popular, right, stack-wise. We could stack, okay? So we had switch stacks, okay? And I love switch stacks, okay? I'm a huge advocate of stacking switches. The 2960Ss, the 3750s, beautiful, right? We could end up having separate physical devices. So we'd take, maybe 3 switches. We'd cable them up kind of in this fashion, right? With stack-wise cables on the back. Give us a relatively decent bandwidth on the back end. But these simulated what? Our control plane, right? So this was actually like our control plane or our back plane between these devices. And we ended up electing one of these guys as the master switch. But the beauty of it, right, was that we could come in, say we had just a single device, we could actually come in, throw many cables to each, right? We could actually have like 2 cables to each because we like to do stuff in powers of 2, right? And that's not powers of 2, so we could throw another cable in there. But the point is we could do multi-chassis ether channel. We could bundle all of those together. Because from this switch's perspective, this over here was one cohesive switch, okay? This was one switch that we were connecting to, not 3 disparate switches, okay? So from our perspective, we could have one of these guys completely fail on us, okay? We could have this top switch die, okay? This master role would go away, another would take over, okay? But we'd still have a bundle of 4 links down here, okay? So we've maintained our connection even through a physical device failure. Again, I was a huge advocate, still am to this day, of Stackwise, okay? Throw these in an access closet any day of the week, because what else do you gain from this setup, guys? What else do you gain by stacking these 3 switches? A single point of management, right? We have one point of management, so I'm going to use POM for short, that we have to go into, one SSH connection, to manage all of those ports, okay? If these were each 48 ports, that's 48 times 3. I don't know what the math is right off the top of my head. But we can come back, we're managing triple the number of ports that we would on a single device, okay? And we could have up to 9 of these in a stack, okay? So we can greatly expand our port density while keeping that single point of management, okay? Now the other thing, the VSS, I'm also a huge advocate of. VSS allowed us to take 2 6509s, right? As long as we had the SOUP 72010Gs, what we could do is form some links in between maybe the 10 gig link on the supervisor and maybe a line card, right? This would end up being what we call our virtual switch link, okay? This virtual switch link was also simulating our control plane. Okay, so this VSL simulated the control plane for us, and what this actually did, much like the Stackwise, is it merges the control plane together for both of these switches. Okay, so again, using 2 6509s, we look like one physical or logical switch, I should say, and we still have one point of management, okay? Whichever one of these is the active VSS member is actually going to be the point of management for the entire system, okay? So where we previously had two disparate systems, each with a single supervisor in it, we now had one logical switch with dual supervisors. Okay, we had the ability to do HA, so we could do a stateless switchover, okay, non-stop forwarding using this system. Now they've developed it where we can actually have 2 SOUPs per system for a quad SOUP logical chassis, okay? But what the pitfall is for a lot of people with virtual switching system is that it shares a control plane, okay? So one of these switches is doing all of the decision making for both of these switches. Okay, this active switch is actually the active control plane member. So again, that's going to be the one we're going to be SSHing. When we SSH to the HA address for these guys, we're going to be going to that active switch. Okay, but from his perspective, he's managing all of the line cards not only on this switch, but also this one. Okay, so again, we have the ability to throw another switch down here and dual home it to both of these, and they can be in one logical port channel. Okay, so again, we could have a catastrophic failure on one of the 6509s, and the other one would pick up that role and continue to forward traffic. Okay, so again, we get that benefit of having multiple upstream switches. Okay, but like I said, a lot of people don't like this shared control plane functionality. I've deployed VSS quite a few times, both on the 6509 and on the 4500Xs. Okay. I love VSS. I think it's an awesome system, okay? I've deployed VSS in a capacity where we've migrated over an entire casino from dual 6509s running HSRP over to VSS. We didn't drop anything, okay? We migrated them completely over to VSS without affecting traffic flow at all. I mean, granted, while we converted one switch, all the traffic failed over to the other one, but we did not affect traffic flow. We did not stop it, okay? We brought VSS up, and as far as I know, we never had any problems with it while I was still with that organization, okay? So VSS ran fine. We got all the benefits of multi-chassis ether channel, but again, we had that shared control plane, which a lot of people don't like, okay? So what happened is Cisco moved and they started creating what we call virtual port channels, okay? So we're going to talk about VPCs, and I'm going to try to do this out in a little storyline, okay? Because one of the main differences between VPCs and these other technologies that we've talked about is that virtual port channels include 2 peers, okay? So we're going to have 2 and only 2 peers within our VPC domain, okay? But they're still going to operate independently, meaning there is no shared control plane between the 2. They still make their own decisions on what they're going to do with traffic, okay? It's not a joint brain kind of venture, all right? They operate independently. So what's going to happen is we're always going to have 2 devices of similar make and model, guys. So we're going to have, say, a 5K and a 5K. Okay? These 2 5Ks are going to form what we call a domain. Okay? So we're going to circle these. This is going to be a VPC domain between these 2 peers. Okay? So we have peer 1 and peer 2. Now, when we form this domain, when we figure out what peers we want to use, do you guys think that these have to be similar make and model? Okay? Meaning, do you think one of these peers can be a 5K and the other one can be a 7K? What's your guys' thoughts on that? Yeah, you guessed correct, okay? We cannot. We have to have similar make and model, okay? We could do this from like a 54 or 5548 to a 5596, okay? But we cannot do cross-platform VPC. So again, we can't VPC or put a 7K in the same VPC domain as a 5K. It will not work, okay? So we need ones of similar make and model, okay? Now, we do have to share some control information between these 2 switches that are going to form this VPC domain, okay? So we have to simulate a control plane between these two switches so that they can pass these special messages between each other. Okay, that is going to be in the form of a peer link. Okay, so we're going to take, I say 2 10 gig ports, okay, because that is best practice, but technically all we need is 1 10 gig port in a port channel. Okay, I cannot emphasize that enough. We have to have a port channel to put our VPC peer link in. Okay, if you try to implement a VPC peer link on a physical port, it will not work. Okay, the only place we can actually put this VPC peer link command is on a port channel interface. All right, now when we do this, some special things happen in the background. Okay, we're going to start running what we call Cisco Fabric Services over Ethernet. Okay, so immediately we get the benefit of running Cisco Fabric Services over Ethernet. That is what we're going to use to exchange our control messages between the two peers. Okay, we are also going to be running bridge assurance. Okay, so that spanning tree port type network that you guys are so used to seeing in the config. Okay, so the one thing I never got about it is when we configure this VPC peer link, it tells us that bridge assurance is now on. Okay, I wish they'd just come out and say, hey, okay, we also enabled Cisco Fabric Services over Ethernet, yada, yada, yada. They tell us everything they did in the background and be completely transparent with us. But unfortunately, they do not. Okay, so we need this peer link, guys. This peer link is probably the most critical piece to the entire VPC configuration. Okay, if we lose the VPC peer link, we're going to be dependent. We need to find some way, because if we break this control plane link between these two peers, we could have this dual active scenario, this split brain scenario. Okay, so we need to figure out a way to mitigate that or to kind of offset the risk. Now if we move back 2 slides here and we talk about VSS, okay, within VSS we had a separate link. Okay, I don't know if any of you guys have done VSS, but we had what was called the peer keep alive link. Okay, and this peer keep alive link, oh my gosh, I just completely gave that away. This wasn't the peer keep alive link. In VSS, it was called the dual active detection. Okay, so let me scribble that out. Dual active detection. I had my brain on VSS, or on VPC. We had this dual active detection link. Now this could have been a dedicated link between the two. It could have ran over a PAGP port channel. But the point of the dual active detection was to detect if we had a failure on this VSL. Okay? If we had that VSL go down, both switches would think they were active. Okay? So we had a second link, a kind of backup link that we could fall back on. Okay? This dual active detection link. Okay? What that did was tell us, you know, if we lost our virtual switch link between the two, the dual active link would let us know if it was still alive. Okay, so that the other switch could restart or shut down or take some action so that we didn't have dual active switches, okay, because that's a bad thing. So we kind of implemented the same thing in VPC, except in the form of, I already gave it away, the peer keep alive link. Okay, this peer keep alive link, guys, is going to send small little UDP packets every second. Okay, so we're going to send a kind of a hello message over that link every second with a timeout of 5 seconds. Okay, so if we miss that, if we miss up to 3, we're going to consider the peer dead. Okay, again, this is our failback. Okay, because if we lose the peer link, we want to be able to tell if our peer is still alive or not. Okay, because if we lose the peer link but we're still getting a keep alive message, we know that the other or the active switch is still there, and then the secondary switch is going to need to take some action, like shutting down its SVIs, shutting down its VPC ports. Okay. Now, these are the crucial pieces of this VPC domain. Okay. The other crucial thing to build the domain is a domain number. Okay. So we have to figure out some kind of numerical value that we're going to put here. Okay. So we're going to be able to go in and put in, again, I like to use 10. We're going to use something like 10. Now, what does this do for us? Okay? Because let's think about that. Let's take a step back. What are we doing with this technology? Okay? We're trying to be able to come down here and hook something like a server up to both of these guys and run a port channel. Okay? But to do that, we have to make ourselves appear as one logical switch, right? That's the whole point of this, right? We want to appear as one logical switch so that we can kind of spoof our identity to these endpoints so they think we're just one switch, okay? Because that's what port channel logic tells us we have to do. We can only connect to one upstream switch, okay? So how do we do this? The domain ID, guys, plays a large part in this, okay? So what we have is this domain ID is going to help us generate what we call the system MAC address. Okay, so this system MAC is always going to be 002304EE, BE, and then the domain number in hex. Okay, so again, we have 8 bits, 0 through 255, available for our domain ID. Okay, so we're going to take that and we're going to create our domain ID. So again, that's going to be 002304EE, BE, and in this case, if we use 10, it's going to be 0A. Make sure I'm right there, 04BE, yep. Okay, so that will be our domain ID, and both switches will use this, guys. So both switches will represent themselves with this same domain ID. So 04EE, BE, 0A. This is how they're going to represent themselves to this downstream devices, to these VPC connected devices. They are going to use that generated system MAC. Okay, so we have to make sure that when we do a huge layer 2 data center, okay, if you do a bunch of different VPC pairs, try to make them all different. We could run into some big problems if we start doing stuff like back-to-back VPC and we configure the same domain ID everywhere. Okay, so it's best practice to go out there when you deploy these in a data center. Let's just make everything different. Okay, trust me, it makes it easier in the long run than having to come back and redo work. Okay, so we're going to type in, we're going to figure out this domain ID. We're going to hook up the peer link, the peer keep alive link. And what's going to happen is these two devices are going to start to form this VPC domain. Okay? So behind the scenes, guess what has to happen, y'all? We have to have another election. We're going to get what we call the VPC operational primary and secondary switches. Okay? Now we can control who is the operational primary and secondary. Okay? Guess what's going to happen, guys? We're going to have another election. Okay? So we have to configure who we want to be the primary or secondary switches. Okay? And again, guess what value comes into play here? Any guesses? A priority. Very good, Tim. So we're going to have a priority value on these guys. Okay? This priority value, again, we're dealing with a layer 2 technology, right? So what's going to happen is we're going to have a default priority of 32,667. Okay? Lower is better. All right? So if we come in and lower the value on one of these guys, I always use 2,000. You guys can use whatever you want. I have a tad bit of OCD, okay? So I will always come in and on my VPC primary device, unless I'm told otherwise, I'm going to just configure 2,000, okay? When this election happens for these guys, okay, when we first bring up the VPC domain, they're going to look and exchange priority values, okay? So they're going to exchange their actual system max, so their built-in system max, and they're going to append that with the priority value, okay? So whoever has the lower priority will take over the VPC primary role, all right? If they're both equal, it's going to be whoever has the lowest system max. So what's going to happen if we adjust this to say 2,000 is this guy's going to take over the VPC primary role. He will be considered, because we configured him this way, okay, he will be considered the VPC configured and operational primary, okay, because he can technically, and we're going to explain some of these scenarios, if we rebooted this guy, okay, and this secondary switch became the primary switch, okay, there is no preemption in VPC. Meaning, if we rebooted this 5K, this guy would take over the primary role, and when he came back up, he would take over the secondary role. Okay, and it would stay that way until we either bounced the peer link or rebooted the second switch. Now, When that happens, he is still considered the configured primary, but he is the operational secondary, okay? Does that make much sense? So this guy will be the configured secondary, but operational primary, okay? Get used to that verbiage. It's a little weird, but we configured this guy to be the primary, so he's still the configured primary, even if he's operating as the secondary switch, okay? So just get used to that. It's just some terminology that's thrown out in a lot of stuff, and you'll actually see it represented that way in the command line when we do some show commands. We start doing our failover stuff during our demo here in a little bit, okay? So just be used to that terminology. But at this point, guys, even if this server wasn't in the mix right now, okay, if we erased him altogether, when we have done this, when we have our domain ID in there, okay, when we have our peer link up and our peer keep alive running, okay, at the most basic level, we have configured VPC. And this is where I'm really going to tune in and try to get you guys to. What I want to do is show you guys how we can get this up at a very basic level, how we can go in, you know, turn on the features, right? We can make sure we have IP reachability over the peer keep alive link, okay? Configure our VPC domain, configure our keep alive link, okay? We're going to verify, we're going to configure our peer link, then we're going to verify again. Before we ever start trying to configure port channels, I want to get you guys to this base point, okay? Because this is where we're going to start winning, guys. Trust me, this is where we win. We get to that base configuration, then we're going to start layering all those nerd knobs on top of that, all right? What we're going to find out as we go through VPC more and more is that you guys, or Cisco I should say, a lot of these knobs were fixes, okay? So they brought VPC to market and they found a lot of stuff went wrong with it. So they threw in a lot of these knobs, these peer gateways, these peer switches, okay, auto recovery, because they found things wrong with it. And these are fixes for that, but we need to know when and how to implement those. So I want to push those to the back of your mind for now and just get you guys to this point, because this is the important point. Getting this up, getting our order of operations correct, to get them in this stance is critical, okay? So we're going to be pushing that pretty hard. Now, again, we've kind of addressed all of these items up here. We've got it to our base config. You guys know now that this domain ID is going to be huge, huge in the generation of our system MAC address. Okay, so I want to start talking about the port types, and then we'll hit up consistency parameters. Looks like Zane has a question here. So Zane says, so the peer link is used for keep alive layer 2 and other link with red for layer 3. Okay, let's go back. So this peer keep alive, or sorry, this peer link, okay, when we run in true Ethernet mode, okay, this is going to be a layer 2 trunk. I should have mentioned that. Okay, so this will be a switch mode trunk, okay, and it'll be in a port channel, and then the port channel will be the peer link. So it will be used for layer 2, not keep alive, Zane. It'll be used for layer 2 control plane information. So they're going to use it to sync MAC tables, IGMP snooping, spanning tree messages. Okay. This link up here, the peer keep alive link, will be layer 3. Okay. So in some way, shape, form, or fashion, this will be a layer 3 link. All right. Now it doesn't matter how we establish that communication. This can be between two loopbacks, two SVIs. It can be routed ports. As long as they have IP reachability from one to the other, we're good to go. Okay. Now what we do not want in a good scenario is to use something like SVIs. If we use SVIs on these switches and for some reason they're using the peer link, that defeats the whole purpose. Okay, so if we use something like SVIs, we want to make sure that they're actually going over the peer keep alive link. So that would mean that we need to prune them, okay, off of that peer link, all right, and make sure they're only going over the peer keep alive. Okay, so yes, good question. Yeah, as long as you have IP reachability, guys, I can't, again, that's another point I can't stress enough. Always test. Go back to your CCNA days. Make sure that you have IP reachability between your two peer keep alive IP addresses, okay? And we'll go through this pretty heavy in the demo as well. So now we've got to have some ports, okay? We've got our VPC domain up and running, and maybe we have this server here, okay? And we're going to connect this server maybe to port 1 on both of these switches, and we're going to configure them as an LACP port channel, okay? So both switches are going to end up having a member in this port channel, okay? So what it's going to look like is, you know, int E11 channel group 101 mode active. Okay, then we'll go into int PO 101. We'll put